Organometallics are molecules that contain a carbon-metal bond. And this carbon-metal bond is unique in organic chemistry, but it has a high degree of covalency. There are two important organometallic species. Those are the Grignard reagents and the organolithium reagents. These molecules are stable at low temperature. Some of them are stable at room temperature, but mostly stable at low temperature. The Grignard reagents have a structure RMgBr, and the organolithiums have a structure R lithium. And so this bond here, the R magnesium bond or the R lithium bond, has a high degree of covalency. And so we don't designate the R group as being minus and the lithium being plus. We have a shared pair of electrons in between the alkyl group and the metal. And so we'll use these reagents later on in chemical reactions, but the reason we talk about them now is because in order to form them, we involve reactive radical intermediates. And so let's talk about how to generate a Grignard reagent. Let's say that we have bromobenzene. So here's bromobenzene. And if we wanted to treat bromobenzene with magnesium in the zero oxidation state. So this is magnesium metal. The metal will eventually dissolve and you will generate a Grignard reagent. Right? And so I'm going to turn the bromobenzene around a little bit. Eventually you'll get this Grignard reagent. So this is phenyl magnesium bromide. And this is known as a dissolving metal reaction. Dissolving metal reduction. And it's very similar to when we had the dissolving metal reduction in the reduction of alkynes with lithium and ammonia. So the covalent Grignard species is known has a partial negative charge on the carbon atom, partial +2 charge on the magnesium, and a partial minus charge on the bromine. And this reaction is exothermic. We normally run this reaction in THF or ether as solvent. These solvents normally function to coordinate to the metal after it's been formed, and so that stabilizes that Grignard species. But the mechanism for formation of this Grignard reagent involves radical intermediates. It actually involves radical transfer reactions in which you have a transient carbon-centered radical. And so let's draw out that mechanism. And to simplify things, I'm just going to erase the dissolving metal reduction and the THF here. Okay. All right, so let's say we have magnesium metal reacting with the aryl halide. The first thing that we do is magnesium gives up an electron to the carbon-bromine bond, right? And then the other electron moves up onto carbon as a radical. And so essentially what you get as an intermediate is a carbon-based radical here, and then a magnesium-bromine bond, but that magnesium has an unpaired electron. In the second step of the reaction, you're going to get another radical transfer, and so you're going to get now the coupling of the two radicals between the carbon and the magnesium to give you now a new covalent bond. Okay? And so this transient carbon-centered radical right here is a high-energy intermediate, and it's formed in the presence of magnesium. You get 2 electrons being transferred here. 1 electron is being transferred in the first step, and another electron is being transferred in the second step to form this organometallic Grignard reagent. Now, if lithium was used in this reaction instead of magnesium, you would get an organolithium reagent. So let's talk. And so let's say we start with bromobenzene again, and this time we need to react it with lithium. Now we get an organolithium reagent. Okay, now we're going to react it with lithium metal, and so the first thing that happens is that lithium is going to oxidize. Okay, so it's going to become lithium bromide plus a carbon-centered radical. Now notice that lithium is already in the +1 oxidation state. It's making lithium bromide, that salt there. And so we need actually another molecule of lithium, another mole of lithium, in order to get a second radical transfer. And so the second lithium is going to come along. It's going to be oxidized. And so the carbon-centered radical is reduced, and then you end up with your new organolithium reagent. And so in the case of a Grignard reagent, the fact that magnesium is in the second column means that it has 2 electrons readily available in order to become oxidized, in order to transfer to that aryl bromide. In the case of lithium, lithium is only in the first column of the periodic table, and so we need 2 equivalents, or 2 moles of lithium in order to get this reaction to occur. Now, that's how we form these organolithium or Grignard reagents. Both of these reagents are highly basic. One can think of the reactions, the reagents as being highly delta negative on the carbon atom. So that carbon atom is very delta negative. This carbon atom is very delta negative. And so one can think of the carbon metal bond as being strongly polarized, all right, towards the carbon atom. Okay, this means it has a lot of electron density, and so it's very basic. Okay, the magnesium and the lithium are, of course, electropositive. They're positively charged, partial positively charged. And so because of this basicity, they're going to be very reactive in the presence of water or other sorts of labile species. And so let's see what happens if we generate a Grignard reagent and then trap it with water. So Grignard and organolithium reagents will actually protonate to give hydrocarbons. And so here's where we then use our double-headed arrow. We can take our magnesium pair of electrons, grab the proton, electrons move up onto the oxygen atom as a lone pair, and so what you get is an alkane plus the bromo-magnesium hydroxide salt. And this happens in both cases. You get the alkane plus, in this case, lithium hydroxide as the resulting salt. Right? This is because the conjugate base in this case, the OH here, right, has a pKa H of 15.7, right? But the pKa of benzene, if R is benzene, the pKa H of this one is actually 43, and so you'd much rather move towards the products in this case than stay in the starting materials. And so what this is saying is that water is a much better acid than benzene. Following this logic, we can actually take these Grignard reagents. I'm just going to take phenylmagnesium bromide here, and this is a good way of deuterating things. And so if we take D2O, right, so D2O is just, remember, a proton that has an extra neutron, a hydrogen atom that has an extra neutron, so this is the same thing here, we just abbreviate it D. We can deuterate things, and this is kind of important because in the pharmaceutical industry sometimes we try to deuterate molecules in order to understand them a little bit better. Same thing can happen for organolithiums. You can take organolithiums and of course trap them with D2O, and they will of course generate the deuterated benzene. can do the same thing with tritium. Tritium is, of course, a hydrogen atom with 2 extra neutrons. So we'll use lithium reagents and Grignard reagents much later in the semester, but what I want you to know now is how to form them, and they form via radical intermediates.